about the 1D Fdtd, the algorithm that we developed to simulate this, how we're going to implement sources, the various boundary conditions, and then we're going to introduce some inhomogeneities into the equation. First, we're going to look at the formulation of the 1D equations. To do this, we're going to look at here we have the 3D equations, Maxwell's 3D equations for a plane wave in a homogeneous medium that is source-free. So first we're going to derive the 1D equations out of this. To do this, we're going to assume that the plane wave is traveling in the z-hat direction, is an x-polarized TEM wave that this causes h of z and e of z to equal 0. We're going to assume there's no variations in the x-hat and y-hat directions causing the changes of x and the changes of y to equal 0. And then due to the polarization, we want e along x and h along y. This gives us this term here, and this term here, and this term here, and this term here. The next slide will show these equations together, and these are our derived 1D Fdtd equations. So next we're going to have to apply the Yi algorithm to them. To do this, first we're going to have to discretize Maxwell's equations, and then we're going to have to discretize them in space and time, and to do that we're placing the electric and magnetic fields on a grid that are staggered, and then lastly we're going to show the MATLAB implementation of this. So here we're going to discretize Maxwell's equations. To do this, we replace all the derivatives with the central difference equation. Once this is done, you can see below here's our discretized Maxwell's equations. Next, what we're going to have to do is solve these so that we're looking to solve the next step in time. And that's when we get these equations here. Here you can see this is n here is the time step. N is time and k is in space. So here we have this one being n plus 1, and you can see here all the other n terms in time are all previous to this one, and same here for the h field. We have n here being n plus 1, and all the other ones are looking in previous time steps. What this looks like on the grid is like this. Here we have e of x represented by stars and h of y represented by circles. So when we want to solve for, let's say, this position in time, we're going to end up adding, here, just 2 seconds, we're going to end up adding this one, subtracting this point, and adding this point. And that's going to go along all the way. So we're going to end up adding this one to here, subtracting this one to here, and then adding this one to here. And then when it comes to solving for the h field, same thing. We're going to add this one to this point, subtract this one to this point, and then add this one to this point. And that is the essentially the Yi algorithm there. Next, we're going to show how we implement this in MATLAB. We implement this in MATLAB using these two lines of code here. The first line here is solving for the EX field, the E field, and the next line is solving for the H field. Here we have NZ is my total pixels in space, del Z is the size step in space, del T is the size step in time. Del T is chosen using the Courant condition. Del T is less than del Z over C, where C is actually just the speed of which the wave is traveling. Here we're going to assume it's the speed of light, and then to thoroughly satisfy it in our code we're going to use 2 times C. So our del T is actually equal to del Z divided by 2C. The E field here is the relative permittivity, and the U field here is the relative permeability. These two lines are then put into a for loop, and that for loop is going to be the steps in time. So each time it's going to step through, and it's going to be solving the wave for the next step in time, and then drawing it. But first, in order to see this, we're going to have a source as well. Otherwise, it's going to be a flat line. To add a source, we need to add that J term here to our initial 1D equation. Here I'm just showing it for the electric field. Now once we add this to the discretized version, we end up getting an equation that looks like this. And then to implement this in MATLAB, we add a new line of code where we're going to emit the source at a position source 1, which is defined in my code. And here we're just going to have a single pulse, and that looks like this. And we can see here, when it gets to the boundary, it's going to flip. And then once it gets back to the source here, it's going to end up breaking a little bit. And that's not really realistic. So the next thing we need to do is show create a way that the wave can just pass right through where the source was. To do this, we create an additive source, and we add this term right here, which is going to allow the wave to just pass right through it, and that looks like this. And you can see now it's just going to continue on and pass right through the source, whereas before it just reflected it. There are a few different types of pulses we can use: Rickers, Gaussian, and continuous. Next we're going to look at the continuous one, and we're going to create a one-way source with that. To create a one-way source, we need to add an add a magnetic source as well. What this does is on that E grid is it causes all the E fields that are being calculated to be cancelled out by the H field, and that way we just get a source that is emitting in one direction. And what this looks like is right here. We can see a sine wave emitting in one direction. Now, due to the half step in the grid, we get some leakage back here. So that what we need to do next is we need to eliminate that leakage. In order to eliminate that leakage, we have to add we have to shift the EX source back so it's in line with the H source. And to do this, we have to account for the time step and the spatial step. To account for the time step, we use this right here. We use omega times the time step divided by 2 for the half, because it's a half step in time. And then to account for the spatial step, we use pi divided by a factor, where the factor for me is my del z is equal to my wavelength divided by a factor, which is just defines how high resolution the my spatial steps are. So we got, and then to get a total offset, we have we add them together, and then we're going to subtract that from the sine wave source, and we end up getting a wave that looks like this. And here we can see that the leakage has been eliminated and it's essentially flat. There is a very, very small amount, but you can't see it here. Next, we're going to create boundaries that absorb the waves, because in real life situations, most of the time you're not going to have it. You're going to want to look at it, and you're going to want to look at the source and see it continue to emit, not reflect back at you. To do this, we have to set the E field and the H field to what the previous values are, so that the E grid doesn't continue to calculate them. Rather, we're setting those values to what was there previous, causing it to look like the wave is just going to continue to travel on, rather than calculating it and having them reflect back at you. What this looks like is this. And you can see now, once this wave gets to this boundary here, it's just going to continue on with no reflection. The last type of boundary is a periodic boundary, where the wave will enter into one side and come out the other side. To do this, we save what is at the beginning of space and set that value to the end value, and then set the end value to what was saved as the beginning space step, essentially causing it to come out the other side. And what this ends up looking like is here. And now we're just going to use a single pulse to simulate this, and as it enters this boundary here, we're going to see that it's going to end up just coming out over on this side here. And yep, there it goes. Lastly, we're going to introduce some inhomogeneities into the field. To do this, I'm just going to set that E field and that U field. For a slab, I'm going to change the values there to simulate the wave entering a piece of glass. In the simulation, I'm going to show you there's going to be two lines that are going to show where the slab of glass would be, and we have the permittivity set to the relative permittivity set to 1.5. When we run this simulation, we end up getting something that looks like this, where you can see here as it enters, it's going to cause a little bit of reflection back, and then it's also going to slow down slightly. Can't really tell here, but it is slowing down a little, and then it's going to continue on. It's also going to reflect at the boundary. Lastly, we're going to talk about conductivity. To add conductivity of the material, we're going to add these sigma terms here. And then that is going to cause our signal to attenuate in that slab that we saw previously. Now, if we just add the sigmas to the electric field, there's going to be a small amount of reflection. So we add them also to the magnetic field. That eliminates the reflection that's going to come back off the material, and will cause the wave to strictly just attenuate in the material, which we can see here. And as this wave comes into the material, we're going to see it attenuate with very, very minimal reflection. This can also be used to simulate an absorbing boundary by setting the sigma higher so that it comes out as completely zero, and then putting it at the end there, and we can simulate an absorbing boundary. That concludes this lesson on 1D FTDs.